So hello everyone, welcome to our next talk in Security Dev Room, and it's Stefan and his talk about secure logging with syslog ng. So let's welcome.
Thank you. So yeah, I'm going to talk about secure logging with syslog ng. That's a project that we performed at Airbus, but of course we profited a lot from the open source community, and I hope that you will also enjoy what we've enjoyed when using this development model. So I'm going to talk about forward integrity and confidentiality, and before actually coming to the topic, I want to perform what we want to protect against. So what is actually the threat model that we want to protect against? So forward integrity and confidentiality is about securing the log host against attackers that gain full compromise. So currently, if an attacker is able to compromise your system fully, he can mess up the logs and tries to hide his traces. For example, he can delete files, he can delete individual log entries from your file, he can even alter individual log entries, and you will never notice it if you have any security mechanism attached to your log file. The problem is typically you open a log file, you can delete one line, you will never know that it was there originally. So that's what we want to protect against. In addition, we at Airbus, you know, we are producing aircraft, and aircraft are not always connected to a network. They are connected to a network sometimes, those through specific protocols, but they are also disconnected. So when an attacker, for example, is compromising our system that's airborne, which is on board the airplane, so there is no connection. So we want to protect it also when it's airborne, and typically in our operational model, log files get offloaded off the airplane when it's at the airport through a series of mechanisms. But typically, we can assume that an attacker, for example, that is on board the airplane is trying to attack our system, so we must also take that into account. So how does log integrity now work in principle? So we have a log host. Here you see a log host. It's an airborne computer. It is a standard form factor for airborne computers, quite different than the ones you used at in a server rack probably. That's an airborne server rack, what you see here. So that's our unit. And it is the log host. So other systems are connected to it, and other systems are providing log records to that log host. So at time T0, we have a log entry L0, and so on. So we have a series of time of log entries. So now what does log integrity mean? So let's assume that at this particular time, somebody is trying to mess up with the logs after having successfully compromised our system. What does the attacker typically do? He will probably delete that log entry. He will probably change the log entry, edit the log entry. And what does that mean for us? So our log file will now have an altered entry. In this example, we changed the log file. So you see this L3 prime here. So the L3 prime cannot be distinguished from what was originally stored under L3. So let's assume that the attacker has gained root access. So we'll probably have a root access on the log. So that root access at that time will be deleted. So how can we know that this was the case? So with our principle now that we've added to syslog ng, we can use a verifier later on to actually verify that this changed log entry L3 was not the original one. So the verifier will indicate that there was a tampering with our log file. What does forward integrity actually mean? You're probably aware of the forward integrity in network encryption, so it's a very similar principles here. So we write a series of entries in the time, and as in the previous example, we compromise at a particular instance of time, we compromise an entry. And then we know that because the attacker has already compromised it at that particular instance of time, everything will be lost, because we cannot rely on what has been written to the log after the log has been compromised. Forward integrity now means that we can still rely on what was there originally. So if the attacker hasn't tampered with, let's say, all the log entries before T3 in this example, we can still use them for forensic purposes, which is great. Because in an old model where we don't have forward integrity, we can forget the whole log. So the question is, how can we achieve that? I'm going to present you the algorithm, so I will not go through all the details. You can read our paper, which is on the FOSDEM website, how that actually works. I will just explain briefly the principle about how this is supposed to work. It's very similar, so some colleagues that I talked to mentioned the word blockchain. That is a very fancy topic. I will not go into that any further, but it's similar in principle. So the basic idea is this. So at each instance of time where you write a log entry, together with that log entry, you write an HMAC, so a hashed MAC for that particular log entry. That MAC protects the log entry. So that means that you encrypt the log entry and you hash it, and you write both to the log record. Now you can say, okay, if we do this for each and every log entry, then do we always use the same key? Because then we wouldn't have forward integrity. And in our example, of course, we don't do that. What we do is we do key evolvement. That means that each individual log entry is encrypted with its own key, and the key is then deleted from the system. And this is what gives us the forward integrity. Because the attacker that would compromise our system at a particular instance of time, of course, has access to a key which is stored in the system, but that key doesn't give him any additional information about what was originally encrypted before that compromise. So now you can say, okay, if I do that, that's nice, but what if I delete, let's say, at time t2, a log entry from my log? How will you notice that? In order to guarantee the integrity of the whole log file, for example, an attacker might either delete an individual log entry or he might truncate the log. We also have to protect the whole log archive. And this is, we do this by what is named here aggregated MAC. So we compute an aggregated HMAC over the whole log file in addition to the MAC that we created for a single log entry. So now, if you delete an individual log entry from the file, we will notice that when we check that MAC. So, and in order to be efficient, we do this iteratively like you see here. So we start with the key naught, which is the individual initial key that is installed on our server when we put it into the airplane. And once the first log entry gets written, we create the key 1. And here you see how the key evolvement is actually happening. So you have the k key I, so the key at instance T3 is based on the key at instance T2. So we derive the key from the previous key. So this is what is similar to a blockchain, so to say. But we also do the same for the aggregated MAC. So this gives us the protection of the whole log archive. Now, how did we implement that? So this is essentially a theoretical example that was also presented at some cryptographic conferences. And what we actually did in our project was to answer the question, okay, this is a nice principle. How can we apply it to the on-board logging system? How can we implement it? And then we came across the syslog NG architecture, which you see here. So we chose syslog NG because syslog NG has a very nice architecture which makes it extensible. And you see here, syslog NG essentially has these mechanisms to extend it. So in the syslog NG terminology, which you can look up also on their website, I put it here, so in case you're interested, you can pull it down from there. It's very comprehensive. They have a source driver, which is a piece of software that actually acquires log records, maybe from a network socket, like in classic syslog. It may be a file, it may be a database, wherever it comes from, it can be fed into the syslog NG system. Then it has a filter mechanism, so we can actually filter and route individual log entries inside syslog NG. And you can also rewrite them. This is the template mechanism. So you get, let's say you get a message in from a database and you want to reformat that message for the output, let's say to a website or whatever, then you can use the template mechanism to rewrite that message. And then you write it to the destination, and the destination can also be everything that you can think of. It may be a database, maybe a flat file, maybe another log relay, another syslog instance whatsoever. So you can create cascades of syslog NG instances like this. And this is what we actually used when we implemented our cryptographic extension to syslog NG. We used the template mechanism and implemented a template into the syslog NG. So the good thing is that we can benefit from everything that was already there. So we have all the source drivers, we have all the filters that we use. We just insert a template there in form of a plugin, which is essentially a C API within syslog NG. We write that, we add the two files as you see here. So we have the key file and the MAC file. And then we write it to the destination. So in our case, we already had a syslog NG log host on our airborne computer. So this was a very, very small change because we only needed to replace the binary essentially, so to add our plugin there. And then we had to change the configuration in such a way that it would include our template. So how does this typically look like? I just created a very small example for you to have a glance about what that means. So these are some random log messages, so to say. They come in at the source. And then you see the encrypted messages like these. What we added here in addition, but that's mostly for computational convenience, is a counter. So you see the colon there, and before the colon, we actually have a counter. So when you now create the plain text at the verifier's end, it will look like this. So the counter is convenient for us because, of course, because for each log entry, we have our individual key. And if we want to trace the key file, we also put that counter into the key file. So how would that look like if you configure it? Well, this is very simple. So you see here a minimal syslog ng configuration file. It's not very fancy, doesn't use any filters. But you see here, there is a network source, so standard syslog. And here you see our template. That's everything what we added. And we didn't need to write any configuration file code or configuration file parsing code. Everything was already there. So we just used the interface of syslog ng. So what you see here is the syslog, which is the secure logging template that we added. We have two. Oh, you don't see the mouse. Okay. So you look at the template line there. Then you have the syslog -k, which is the location of your key file, so where you store it. The -m is location for the MAC file. And that $raw message gives you actually access to the raw log message that was received at the source. In order to get that macro filled, you have to add this particular flag, which is called flags store raw message, because syslog ng by default parses everything that it receives at the source into a syslog conformant message. And for encryption, we don't want that. So we want the raw message to be also encrypted. So that's why we add it here as a raw message. And that's it. And then we have a log entry. You see it here. The source is just the network, and the destination is our local log file. So this is everything what we need to do in order to work with our code. So how did we implement it? Just to give you a small example about the amount of effort that we put into it. So I don't know if it may be hard to read, so you can read it on the paper, which is on the FOSDEM website. So this is the source tree of syslog ng, or part of it. And this is where we added our source files. So in addition to the source files existing, so we had only 6 new source files to add. Why? Because most of the crypto code that we use relies on OpenSSL. And OpenSSL is already present in syslog ng because it's also used for other plugins. So we essentially, all the crypto functions that we use are in the lib directory, and the template code is in the modules directory. So that's where we would look at. We had no new dependencies, so that means other than OpenSSL, we don't need any new dependencies. So if you want to compile syslog ng with our code, then it's very easy to do. This is already said, and in addition to that, we did a lot of performance tests because we didn't want to impair the performance of our airborne computer, where we are resource constrained, of course, in terms of power. And we relied on AES-NI, we already talked about this, in the Intel CPU that we use. We use a Skylake CPU in our airborne server. So there was no performance impact for the log entry. The only impact that we had was the file I/O for the 2 small files. So just to give you some numbers, so on a development machine with these parameters, we were able to digest about 9,000 log entries per second, which is much more than we normally have in normal operation. Typical log entry on our log host is about 200,000 log entries in 24 hours. So that's what we have on a normal airplane. If you extrapolate this to 1 year, you will have about 73 million log entries per year. And still, we can do the key derivation in less than a second. So that's very, very, very efficient. Of course, we also had to face some challenges. The first is the log system behavior under load. You all know this. So if you use a log system that uses network sockets, then you have the reliability problem. So if you have too many messages coming in, you will either lose messages directly if you use UDP, but even if you use TCP, you can lose messages. If you don't want to lose those, you can resort to things like the RHEL protocol by the syslog guys. which adds a layer 7 reliability on it. But even then, you have the challenge to face that you might lose messages. For us, it showed in the test that yes, but this is normal behavior even if our module is not included. So if you have plain syslog NG, you will have the same problems. So it's not worse than we were before. A major challenge was the syslog NG API, which is not very, very well documented. So we really had to read the source code, debug through the source code in order to know actually how the plugin interface is supposed to work. That was a bit tedious. So no developer's guide was available where you can just say, okay, this is the API. If you want it extended, then you do these steps. This was not there. The build system also was quite complex. So it was not so easy because syslog NG is a very comprehensive system with a lot of plugins, and you need to strip it down in such a way that you can easily build your own code. And that was also not so very, very easy to do because also the build system was not well documented. It relied on the GNU tools, of course, and you know how those work. But if you just want to, for example, compile your own plugin, you had to do some handwork. And the packaging, of course, had to be done manually. The syslog colleagues, they supply a spec file for the RPM-based Linux distribution, which is what we use on board the airplane. But we had to tweak with this as well, so that was handwork, more or less. A very important thing to note is also that we will have no lock rotation, because you can think of having your cryptographic chain where you chain your log entries together and you have the overall integrity tag on the whole log file. So if you now rotate things, then you will delete content from your log archive. You cannot verify the log any longer, because you delete something from the crypto hierarchy. So you have to be careful about lock rotation, not to do lock rotation anymore. So if you use syslog NG with any lock rotate, you have to get rid of lock rotate. What we do on the airplane, for example, as we have limited storage anyway, what we have to do is to offload the logs down to our analysis tool and then do the verification there and then continue logging with the crypto log. An example scenario, how it would look like in our operation. So we have an airplane which has an onboard log host, like in this picture. That's actually the real box that flies on A320. So if you happen to fly on A320 from or to Brussels, you will probably have that box on board. And on that box, we do the keyword derivation and we do the log record creation. So that box is actually running our crypto log extension of syslog NG. And when the airplane lands at the airport, there are different facilities for transmitting data from the airplane to the infrastructure. So in this example, it may be an access point. So we have a wireless connection between the airplane system and the airborne infrastructure. And from there, we will transfer the logs into our security information and event management environment, which in our case is a Splunk environment where we then can integrate the verification in, and then we can do the normal log analysis as we've used to. And that brings me to the summary. So we achieved a system that is industrial ready because we have it on board the airplane. It has passed a lot of tests. We have colleagues who did some very interesting and deep tests on the system before we actually put it into production. We have a minor change to syslog NG, so everybody who is actually already using syslog NG will enjoy that it does not bring a great effort into to benefit from forward integrity in log files. We can do the verification offline, so even if we have a small resource constrained airborne system, it's not needed to do the verification on board, so this is separate. So we offline the logs, offload the logs, and then in the ground infrastructure we can use more computing power to do the verification. And in the future, what we intend to do, and we just started to work on that, it's also an exciting project, is to extend that into a system which can also recover from crashes. So think about your log host crashing, and because of buffering, you might lose log entries. If you now have a crypto log, then of course the verification will complain because you might have lost some data, which is okay because you have lost them, so your log is not complete. What we will now do is extend what we've already done for the tamper-evident logging here. We will do a crash recovery with a particular efficient algorithm that is storing the data in a redundant manner. Approximately about 11% increase in storage will give us crash recovery. So that means that if somebody crashes the log, even deliberately as an attacker in order to mess up the logs, we can recover those. and still benefit from cryptographic integrity. And that brings me to the end. Thank you. So these are the languages I accept questions in.
How do you decrypt? Is that tool a command line tool?
Yes.
Okay. How you decrypt? Do you have a command line tool for this?
Yeah. So what you call decryption, we actually call verification, because it's not simply decrypting; it's also checking all the hashes. And for that, we provide you with a verifier tool, which is a command line utility. So that's part of our package. So if you build it with syslog-ng with our patch, you will get that command line utility. And you can use that command line utility in your scripting environment, wherever you want to verify the logs. In our case, it's of course always on ground in some analysis environment. It's not on the airplane. So it's detached. So you have on one hand, you have the log host, on the other hand, you have the verification tool, the decryption tool.
Just which Linux distribution you are using on the log host?
So in our case, it's Red Hat Enterprise Linux 7 with our own custom-built environment for the airborne environment. Of course, you can think about it's a resource-constrained system where we need to strip down the distribution. This is my development machine, so I build it on the Fedora. Yeah, it builds on every Linux. I also use it I build it on OpenBSD successfully, although you have to patch it there. But that's not because of our code. That's because of syslog-ng needs patches and for OpenBSD. So it builds on a lot of open systems.
Thanks for talk. I have a question on, so you said one of the key properties that allows this mechanism to work is to delete the old keys. But I wonder, do you just store them in memory and realize that it's just not going away, or do you write them to files, or?
Yeah, for reliability reasons, we write them to files. So I can probably switch back to the picture here, just to give you an idea. Where is it? So here you see there are two small files that we write. One is the key, and the other one is the MAC. So the problem is that if the system somehow has a power interrupter, so you will lose your key, and then you cannot continue anymore. In our case, we will resort to plain text logging in order not to lose any log information.
But do you then write for each step, like each log line, you overwrite basically this file?
Yes, yeah. And this is of course the main performance impact that we create, reading and writing of small files. It's a 56-byte file.
Okay. And another question, the template that you've shown, it looks a bit like it looked like a string with like bash inlining and then line ending. So is it actually, do you actually call a sub-process all the time, or so it template and then braces and parentheses?
Yeah. So this is not a sub-process. It's actually just a function call. So in syslog-ng, if you program a template, because it's not in C++, it's plain C. So there is a magic macro which essentially extends this into a function call, which is particular to the template, and then calls your template, whether it finds an entry in the configuration file, your function is called. Okay. So that's very efficient. This is in contrast to our syslog. They actually do a fork exit.
Yeah, okay, thanks.
We've got maybe 1 minute for last question. Okay.
Okay, it should be quick. During the presentation, you mentioned that it doesn't support log rotation. Is there any particular reason why, or is there any feature that could be similar to that log rotation?
Yeah, so log rotation will not work anymore because each log entry is cryptographically linked to the next one. So if you rotate the logs, you actually delete them. And if you now want to do the verification, then you have to do the verification from the starting point. So you start at K0 with the first key, you decrypt the first entry, you evolve the key to the second one, and so on. If you now delete all the entries in between, you cannot no longer verify the logs because there are no hashes to verify. So you can no longer use log rotation. That's basically part of the principle. If you need log rotation, if you need to care about space, as we do on board the airplane, for example, you can imagine that on board the airplane we don't have much storage space. you need to offload the logs. So the thing is that you can generate a signal when, let's say, 80% of your storage space is exhausted, and then you will generally offload the logs and then verify them offline in another environment where you have more storage space. So pull them off the log host.
Thank you. We are out of the time, so thank you for your talk.
Thank you.